Welcome to another class. Today we will be looking at deflection of statically determinate structures. We are going to be making use of the virtual work method, which is also called the unit load method, and we're going to apply this to trusses. We are going to look at other structures as like beams as time goes on. We're starting with trusses. So the unit load method is basically a method that is used to analyze the displacement in structures or the deflection in structures, which is also displacement due to due to internal stresses and all the stresses that acts upon the structure. So the basic concept of the unit load method is that at the point where you want to check the displacement, you apply a unit load. So these are some background material you can go through before the example, and this is the procedure which we will look at using an example. So this example before us says determine the vertical displacement of joint C of the steel truss shown below. The cross-sectional area of each member is a area equals to 3.2 times 10 raised to the power minus 5 meter square, and our modulus of rigidity, elasticity rather, is 1.9 times 10 raised to the power 9 kilonewton per meter square. We are given this truss before us with loadings. So what we do first is we obtain the virtual load by applying a unit load, okay, at joint C. So the next diagram shows us that. So we apply a unit load at joint C, a unit load at joint C, because that is what that's what we are trying to that's the joint we have been asked to analyze. So we apply a unit load at joint C. So let me say obtain, apply a unit load at joint C. So when we apply a unit load at joint C, we find the reactions. So to find your reactions, we say summation of forces of we look at the moment about point A equals to 0. If we take this as our positive direction, it's just the same analysis just like we've been doing. Take this as our direction. We have one, we have 1 times 6 equals to RD times 9, right? So RD equals to 0.667 kilonewton, okay? So we get RD as 0.667 kilonewton. If we do summation of forces in the vertical direction, summation of Fy equals to 0, and we take this to be our positive direction, then we have Ra plus Rd equals to 1, okay? And so we end up having our Ra to be equal to 0.333 kilonewton. So this has been done to obtain the angle, okay? So this is three this is to obtain the angle between the trusses. So having done that, we move to analyzing the different joints in the truss using the method of joints like we've learned in the earlier class. So if we consider joint A, we consider joint A, and we say this is this. We consider joint A, and we pick that as our direction of force. This is joint A. So we have FA, we have FAB, and we have RA, which is equals to 0.333 kilonewton, right? That means if we say summation of forces in the vertical direction equals 0, and this is our positive direction, then we have RA minus FFA sine 45, right? We found sine 45 degree equals to 0. So we have RA to be equals to 0.33, right? Equals to FFA sine 45. Therefore, FFA would be equals to 0.471, which is in compression. Since our direction we picked earlier was compression and our answer is positive, it means our direction is correct. So compression. So if we then take summation of forces, still considering joint A, summation of forces in the horizontal direction Fx equals to 0, and we check that, we will say FFA cos 45 will be minus FAB equals to 0, right? So we then have, so that's minus FFA. So we then have minus 0.471 cos 45 equals to FAB. So FAB is equals to minus 0.333 kilonewton. And our initial direction for FAB was in compression, which means, and since we have minus, it means our direction is wrong. So FAB is actually 0.333 kilonewton. So instead of compression, it's tension, because our initial direction we chose was tension in compression, and our answer is negative, which shows that we need to change our direction. So if we consider joint F, if we consider joint F, if we consider joint F, we have this. We have this. We have FFE, we have FFB, and we found this to be 0.471 in compression. So if we take the summation of movement in the vertical direction, summation of movement in vertical direction, and this is our positive, it means we have FFB plus 0.471 cos 45 equals to 0, right? And FFB would then be equals to minus 0.333 kilonewton. We would do the same thing, FFB equals to 0.333 kilonewton in tension, not compression anymore. Okay, so if we take the other direction, summation of moment in the horizontal direction equals to 0. It means FFB, we have 0.471 sine 45 equals to FFE, right? So FFE will be equals to, when you do that, 0.333 in compression. Okay, so if we check another joint, if we go for joint B, if we go for joint B, we go for joint B, we go for joint B. If we check joint B, since we have already gotten the directions of all of this, we use their direction. We use the direction we've gotten in our previous solution. So this is 0.333 kilonewton. This is FBC. We have this also acting. We have FBE, which we've already obtained, and then we have this as 0.333 kilonewton. So summation of forces in the, let me clean that, kilonewton. So summation of forces in the vertical direction. So summation of forces in vertical direction, we have 0.333 plus FBE sine 45 equals to 0. So if you calculate that, you would have FBE to be equal to minus 0.471 kilonewton, which we would revert the direction to be FBE to be equal to 0.471. So instead of it to be in tension as it was drawn earlier, it then becomes compression. Okay, I hope we remember all of these things. We've talked about it. So if we consider this other direction, summation of moment in the horizontal direction, we will obtain 0.471 cos 45 plus FBC equals to 0.333. Okay, so FBC, if you solve this, FBC becomes 0.667 in tension. Okay, so if you consider another joint, say considering joint E. Yeah, if you consider joint E, joint E, the last one we considered, this was joint B. Let me write it there. Considering joint E, we have this. We say this is this, this is this, and this. We consider joint E. This is joint E. This is 0.333. This is 0.471. This is FEC, and this is FED. So if we say summation of forces in the vertical in the horizontal direction. We say summation of forces in the horizontal direction. We are going to have, let me demarcate this. We are going to have 0.333, sorry, I'm trying to manage space, plus 0.471 sine 45 equals to FED sine 45. Okay, so FED then becomes 0.942 kilonewton in compression. Okay, so considering the vertical direction, what do you call it? Um, vertical direction, I was correct. Considering the vertical direction, let's say this is a positive, right? If this is a positive, Fy equals to 0. Okay, so that will be 0.471 cos 45 plus FEC plus FED cos 45 equals to 0. Solving this, you will get FEC to be equal to approximately 1 kilonewton in tension. Okay, which means it's negative. So when you revert the direction, it becomes tension. So that's that. I'm trying to manage space. If we consider another joint, um that's joint, if we consider joint C, so joint C. Now let me demarcate this. If I consider joint C has just one component. So putting everything in the directions we have obtained, so we will consider joint C. This is joint C, and this is 0.333. This is FCD. This is 1 kilonewton as we have obtained. This is 0.667. So the only thing we are looking for here is FCD. So if you say force summation of forces in the horizontal direction equals to 0, that means we have FCD to be equal to 0.667 kilonewton in tension. So after you have gotten all of these forces we've gotten, you bring them and arrange them in the truss, right? This all of this now becomes our virtual force N. Virtual force N. Okay, this is our virtual force N. Everything we've gotten, all the values, we just put them. The ones in the negative are compression. It means this is compression. When you see it in negative, it means this is compression. I hope you should know that by now. We've done a lot for you to know that. And this is, every positive is tension. Okay, so but the main thing you should notice that this is our virtual force. So now we go on to calculate our real force. We go on to obtain our real force. Yeah, so to obtain your real force, you analyze this truss using the real forces like it came in the question, right? So we have finished with the unit load. So now what do you do? First of all, you calculate the reactions, right? Calculate the reactions, okay? Calculate the reactions. So from what we've been doing, that's if we take moment about A, we have our reaction to be 18 times 3 plus 18 times 6 equals to RD times 9, right? So RD will be equals to 18 kilonewton, okay? 18 kilonewton. So summation of forces, if we take the summation of forces in the horizontal direction, not horizontal, vertical direction. It's vertical. It's vertical. In the vertical direction, if we take in the vertical direction, Fy equals to 0. So we have 18 equals to FFA. Let me put it this way. You have RA plus RD equals to 18 plus 18, right? So RA, if you do this, RA will be 18 kilonewton. So now remember that this is a pinned support, right? So it has also an horizontal component, Rx. So summation of forces in the horizontal direction, positive equals to 0. Rx, there is no other force coming countering, so Rx equals to 0. So we've gotten the forces. We analyze the joints just like we did in the previous virtual load. If I take for instance joint A, that's 18 kilonewton, and this is FAB, and this is FFA, right? If I say summation of forces, in the vertical direction equals summation Fy equals to 0, that means 18 equals to FFA sine 45, right? Sine, let me clean that. FFA sine 45 sine 45. So FFA becomes 25.46 kilonewton in compression, okay? So summation of forces in the horizontal direction, that means FAB be equals to FFA cos 45. If you solve that, you have FAB to be equal to 18 kilonewton in tension, okay? So you go over all the joints like we did in this first one using the same method of joint, and when you finish analyzing every of these joints, you analyze um joint F, B, E, and C, like we did with the unit load, right? That like we did with the unit load, you would obtain this as your this will now be your real forces. Real force N. This will now be your real forces N as arranged. So now we take these real forces and apply them to the virtual work equation. Okay, we apply the virtual work equation. The virtual work equation says that one this one would is the virtual load applied, and it is in the unit of the forces. Okay, so that's 1 kilonewton times the displacement is equals to summation of virtual load, virtual force times real forces times the length all over area times your modulus of elasticity. So we arrange every of those members on the table, right? Member AB, for the member AB, you take the real force, the virtual force of for member AB, you take the virtual force of AB and the real force of AB and the length, and then you multiply all of this to get this last column, right? That's what it is there. Let me show you something. So for member AB, if you check virtual force AB, this is AB. AB is 0.33, right? If you go over to the real force, AB is 18 kilonewton. So we just brought 0.33, 18 kilonewton, and the length between them is 3 kilonewtons, right? You put that down. For member DE, you use the angle to find the length, which was found to be 4.31. I believe you can do that from what we did in the last class. And then the summation of these forces, right? The summation of these forces gives us this. So at the end of the day, our displacement is this. That's 335.14 kilonewton square meter all over the area we're given 3.23 times 10 raised to power minus 5 meter square times 1.9 times 10 raised to power 9 kilonewton per meter square. At the end of the day, we obtain our deflection, because this is going to go for this, right? This will go for this, and mm, am I right? No, it won't cancel it. Sorry, it won't cancel it. When you try to divide, it won't cancel. It will multiply with it. It will become kilonewton square. So both of them will cancel. So all of this will go. Just know all of this will go, right? Then this will go for this, right? So at the end of the day, we are left with our deflection to be equals to 5.46 times 10 raised to power minus 3 meters. Okay, so that's that about virtual work. I attached the hand calculation sheet to this. and I would still send the PowerPoint as I've been doing. Please always go over these videos with the calculation sheets I send to help you understand, because some of the calculation sheets also contain assignments and possible corrections to errors in the video. So please go over this, and I'll also send the it in the PowerPoint form. So thank you. The next video I'll be sending will have to do with virtual work method using on beams, not trusses. So you can also study further using the textbook I shared in class, Structural Analysis by Hibla, RC Hibla. Okay, so have a nice day. Thank you.